Hello all. In this lecture, we will start learning metaheuristic algorithms. We will first start with definitions of metaheuristics, and we will compare metaheuristics with local search algorithms. What are their similarities? What are their differences? And we will learn the advantages and disadvantages of metaheuristic algorithms. So this will be an introduction into metaheuristics, and in the following lectures we will see several examples of these metaheuristics, such as tabu search, simulated annealing, and genetic algorithms. So let's get started. The concept of metaheuristics is introduced by Glover in 1986. So we can call these solution techniques as rather new techniques, and the evolution of these techniques depends on the evolution of the computational power also, because heuristic algorithms and metaheuristic algorithms require computational powers, and they are adapted or implemented in computers. These metaheuristic algorithms are generic heuristic solution approaches that are designed to control and guide specific problem-oriented heuristics. So metaheuristics are also heuristic algorithms. Sometimes they are called heuristic algorithms with additional features. So we will talk about it later on. They usually have the same idea of improvement algorithms. They take an initial solution and they improve its objective function value, like the local search algorithms. But the local search algorithms stop at a local optimum solution. When they encounter a local optimum solution, they stop. But metaheuristic algorithms do not stop. They try to avoid these local optimum solution in order to find the global optimum solution. These metaheuristic algorithms are often inspired from analogies from natural processes. So we will see about these, for example, genetic algorithms, ant colony algorithms, simulated annealing algorithms. These are all inspired from natural processes. There are different definitions for metaheuristics. So for example, one definition says that a metaheuristic is an iterative generating process controlling an underlying heuristic. So there's an underlying heuristic, and this metaheuristic controls this underlying heuristic. And how does it control it? By combining various strategies in an intelligent way to explore and exploit search spaces. Okay, so we are exploring the search spaces with different strategies, okay, to find near optimal solutions in an efficient way. So when we make examples, what these definitions mean will be more clear. Another definition of metaheuristic says that it refers to a master strategy that guides and modifies other heuristics to produce solutions beyond those that are normally generated in quest for local optimality. Again, you see there is a similarity between these two definitions, both of them saying that there is a heuristic, underlying heuristic, and metaheuristic gives you a strategy to control this heuristic algorithm to search the solution space to find good solutions and escape from local optima to find the global optima. But of course, this is also a heuristic algorithm, and metaheuristic also doesn't have a guarantee of optimality. Okay, they will again stop with a local optimum solution. A metaheuristic, another definition, is a procedure that has the ability to escape from local optimality. Okay, so but still there's no guarantee of global optimality. It means that the best thing that you can say at the end of a metaheuristic algorithm is the result is still a local optimum solution. Okay, so also we said that one disadvantage of local search algorithms is they stop at a local optimum solution. And we said that in metaheuristic algorithms, we try to avoid these local optimum solutions to find better solutions. So it means that we are in metaheuristics, we don't need to move always in the improving direction. Usually in local search algorithms, we find we have an initial solution or we have a current solution. We check the neighborhood of this solution, and if we find an improving neighbor, then we jump to that neighbor. But in metaheuristic algorithms, you may go to a neighbor which is worse than the current solution, so that we can find a better solution. So what is the idea? I can simply sketch it here. Let's assume that we have such a function. Okay, so assume that we start from here our local search algorithm, and according to here, when we check the neighborhood of this solution, so this is the solution value and this is the neighborhood. When we check the neighborhood, we see that if we move in this direction, the value of the solution is improving. Okay, then we take one step, another step, and etc., and we reach to this position, this solution. And when we check the neighborhood, we see that it is the best solution in this neighborhood. So we say that this is local optima and stop. So local search algorithms stop at this solution if we start from this initial solution. But metaheuristic algorithms do not stop. And what does it mean not to stop? It means that you allow, even the neighbor is worse, you allow a move to that worse neighbor, so that you are hoping that you can find a better local optimum solution than this one. Okay, so let's assume you started from here. In local search algorithm, you will find this solution, but in metaheuristic algorithms, you will move, even the neighbors are worse, you will move, continue moving, and then you will find this solution next. Okay, this will be the first solution, this will be the second solution. But you see, the second solution is worse than the first solution. It means that in metaheuristic algorithms, we always remember the solution, the best solution that we find until that time. Because otherwise, if we forget about the previous best solution, we may find a worse solution at the end. But in local search algorithms, the current solution is always the best solution. But in metaheuristic solutions, we have a current solution, but we need to remember the best solution as well. And another issue with metaheuristics we will talk about later is this. Okay, let me sketch another clean one. So let's assume that we have this problem that we want to maximize. We started from this location, this solution, let's say. We jump to any one, and we reach to this one. And we said that metaheuristic algorithms do not stop and it continues. So it comes to this point. So when it's in this position, okay, so the algorithm checks the neighborhood. And in this neighborhood, it sees that if I move to this in this direction, it makes my objective function better. So you continue in this direction and come to this point again. And from this point, you continue in the not improving direction. And then from this point, you go in the improving direction. And non-improving, improving, it means that you are turning inside the same set of solutions. This is called cycling. One of the most important issues in metaheuristic algorithm, or when you allow non-improving solutions, if you allow non-improving solutions, this may result in cycling behavior. So a metaheuristic algorithm must avoid cycling. Why is that so? Because when you solve a problem by hand, you know that this is the same solution, this is the same solution, so you can just ignore it. But when this is the computer, if you say to the computer, always check if you encountered the same solution or not, and etc., it will take a lot of time to make those checks. And the computer will not know if it is the same solution or not. Okay, so it will cycle through the same solutions, and you will assume that the computer is running for, let's say, minutes for to find a better solution, but in fact it's not searching the whole space. It is just cycling through the same set of solutions, and at the end it will give you this solution, and you will say that okay, the computer worked for, let's say, 10 minutes and the best solution that it could find was this. But in fact, for maybe in the half of the 10 minutes or in 90% of the 10 minutes, it just cycled through the same solutions. So you need to avoid this cycling. It is very important. And different meta-heuristic algorithms have different mechanisms to avoid this cycling. So we will see examples of taboo search, simulated annealing, and genetic algorithms in these lectures. And we will see in each one of these how this cycling behavior can be avoided. Okay, so this cycling and the reason for cycling is important in meta-heuristic algorithms when we allow non-improving moves. Of course, there's another issue that we will talk about meta-heuristics as well. How do you stop a meta-heuristic algorithm? Stopping criteria. So in local search algorithms, in improving algorithms, whenever you find a local optima, it means that you check the neighbors of a current solution. If none of the neighbors are better than this one, then you stop. So the stopping criteria is this. You can also stop with respect to some other criteria, but the traditional stopping condition is this. But in meta-heuristic, we do not stop at this point, we continue. Then we find another one, but we do not stop, we continue. So how do you stop? What is the stopping criteria? Okay, so again, each meta-heuristic algorithm should tell us what is the stopping criteria. Also, as we said, since meta-heuristic algorithms are local search or improvement algorithms, then you need to identify your search strategy. It means that how do you define your neighborhood? Okay. This is also important in meta-heuristic algorithms. Okay, so also, how do you find your initial solution? Since this is an improving algorithm, you need an initial solution. Okay, so you need to answer, or a meta-heuristic algorithm must answer these questions. How do you find the initial solution? How do you define the neighborhood? How do you stop the algorithm? How do you avoid the cycling behavior? These are the questions that must be answered by any meta-heuristic algorithm. So meta-heuristic algorithms are not tied to any special problem type. So it means that, for example, you have a taboo search algorithm. It doesn't mean that the taboo search algorithm solves the TSP, only TSP. No, you can apply the taboo search algorithm to solve a traveling salesman problem, a knapsack problem, set covering problem, facility location problem, machine scheduling problem. So any kind of optimization problem, even nonlinear programming formulations, you can solve with these meta-heuristic algorithms. So they are general methods that can be altered to fit this specific problem. So, but you need to alter the algorithm according to that TSP. So it doesn't mean, for example, if you develop a mathematical programming formulation of a problem, for example, TSP, if you formulate it, you can use Cplex to solve it. If you have set covering and if you formulate it, then you have Cplex to solve it. And Cplex always use the same algorithm, which is the branch and bound and cutting plane algorithms, to solve it. If you have any other problem, facility location problem, and when you formulate it, and then Cplex solves it. Again, for TSP, for set covering, for facility location, you can use the tabu search algorithm, but there is no single way of formulating the problem and using the same tabu search algorithm. You need to modify the tabu search algorithm. Okay, so you have tabu search algorithm, but somehow you need to modify this tabu search algorithm according to these specific problems. It is very important in meta-heuristic algorithms. Usually, these algorithms are inspired from nature. Let's see some examples. The simulated annealing algorithm we will see in more detail. It's inspired from the molecule crystal arrangement during the cool down process. So it comes from the annealing process of metals. So if you schedule this cool down process, if you have a schedule for this cool down process, you may obtain material with different properties like strength. Okay? So in order to obtain the best material, you need to follow a cooling schedule. And we will see how this idea is implemented or used in solving optimization problems. Again, in evolutionary computation, genetic algorithms, for example, the principles of biological evolution is used. The crossovers, survival of the fittest, the mutation, okay, all these properties, the chromosomes, genes, all these properties of evolution are used to find the best solution. In tabu search algorithm, memory is used. It's a distinctive feature of the tabu search algorithm, the use of memory, long and short-term memory. In ant colony optimization or particle swarm optimization, individual and group behavior of agents, different agents, are considered or used to solve optimization problems. So we will see examples of such algorithms and how they are implemented or adapted to solve optimization problems. If we compare meta-heuristics with local search algorithms, in local search what do? We start from an initial solution, and at each step we try to improve the solution by making small changes until we reach a solution where we cannot make any further improvements, and at that point we stop. In meta-heuristic, we can use meta-heuristics to guide these local search algorithms to escape from local optima, and as I said, we allow non-improving moves in such local search algorithms, so that we avoid local optima and to improve its value. There are several meta-heuristics which are based on local search algorithms. We will see examples of these. But although they are based on local search, their mechanisms may be different from each other. Okay? We will see examples. We will see examples of simulated annealing and tabu search. What's the reason of using meta-heuristics? What are their advantages when we compare it to improvement or local search heuristics? Meta-heuristic algorithms are very flexible. They can be applied to many different problem variations, to many different sizes of the same problem. Usually, meta-heuristic algorithms find the global optimum solution, but be careful. The thing is, even if they know the global optimum solution, we don't know if it is global optimum or not. So there are tests that we can make if the tests to evaluate the performance of such algorithms, but the thing is, there is no guarantee of optimality. They are still heuristics. They are not exact algorithms. They are usually robust to problem size, problem instance, and random variables. What does it mean? It means this: if you have an algorithm, when you increase the size of the problem, when you use a different data, different instance of the problem, you will still get good solutions in reasonable amount of times. The solution time will not increase too much. But this is often we say it. Why? Because sometimes Metaheuristic algorithms require a large computational time, especially if you do not design it carefully. Metaheuristic algorithms may require a quite long amount of solution time, especially for larger instances. But of course, you can play with the parameters of these algorithms to reduce the solution time. Okay? And in some cases, there are no exact algorithms to solve the problem, and construction and improvement algorithms may fail to find good solutions. So the meta-heuristics can be the only alternative for you to find good solutions for these kind of problems. So they may be the only practical alternative. But there are also disadvantages of meta-heuristic. So you need to know these disadvantages as well, so that before applying a meta-heuristic algorithm to your problem, you will be what are the weaknesses, possible weaknesses of those solution methods. Often these meta-heuristic algorithms need problem-specific information or techniques. So as I said, for branch and bound algorithm, or for when you formulate a problem, you can solve it with a commercial solver. You don't need to know the branch and bound algorithm. That commercial solver, as long as you know how to formulate it, you can solve it. The solution is pretty straightforward. But even if you know the tabu search algorithm, the basic mechanism of the tabu search algorithm, still you need to adapt this algorithm to your problem instance. Okay, and you need to, there is no solver for this. You need to implement that maybe in Java or C++ by yourself. Okay, depending on your design. So in fact, you are designing the algorithm specific to that problem, and it usually takes time. Again, optimality is not guaranteed. It's a heuristic algorithm. Usually there is no theoretical basis behind it. We know that the branch and bound algorithm is an exact algorithm. We know the simplex algorithm generates the optimal solution. We have the fundamental theorem of linear programming. But there is no theoretical basis. For example, in particle swarm optimization, in ant colony optimization, you observe the behavior of the ants in the nature and how they find their food, and you adapt this to an optimization problem to solve it. So are these ants optimizing their time to find the food, or are you able to use their instincts in this optimization procedure correctly? So there is no theoretical basis in many of these methods. Different search may yield different solutions to the same problem. For example, simulated annealing algorithm, it uses a cooling schedule and acceptance of a non-improving move, we will see the details, is probabilistic. So it means that when you run the simulated annealing algorithm for the same problem for the first time, you will come up with a solution. For the same problem with the same data, if you run the algorithm a second time, you may come up with a different solution, a better or worse solution. And at each repetition, theoretically, you can find a different solution. Okay, so it is a disadvantage of these metaheuristics. There is no certain stopping criteria. You need to find the stopping criteria. We will talk about this later on. Okay, but it's important because it affects the performance of the algorithm. And there are multiple search parameters. You need to play with these parameters to come up with the best combination. Okay, so a tabu search algorithm for the traveling salesman problem may work very poor. The performance can be very poor. But if you play with these parameters, after that, the performance can be perfect. Okay, just the parameters can affect the performance a lot. But there is no straight way, there is no way to know what parameters are the best. You need to make a lot of tests on these parameters and it takes time. So it means that implementing a meta-heuristic algorithm to solve a problem takes a lot of time or may take a lot of time. But after that, when you implement it, when you come up with your best design, usually it will find very good solutions in quite short amount of computational time.